So this is lecture 46 by Harvey Friedman on embedded maximality, please.
Thank you. Okay, so there's quite a bit of news, and I haven't quite finished the proof. I got a sketch of my proof of the big thing today is largely done in one direction. The proof from the large cardinals, but the reversal is sketched, and of course I don't do detailed proofs here, anyways. But so therefore, next week everything will be completely pinned down. I couldn't quite pin down all the details, so next week it'll be completely solid. I know I've kept changing what I do with this, but you'll see that it's uh, in a somewhat remarkable condition. All right. So, first of all, I had to change the name of the book to Embeddings in Maximality, Free Choice, and Games. There's a new thing called free choice, which is extremely natural. There's an infinite theory of free choice, just like there's infinite. Right now, embedded maximality is an infinite theory, right? And you know that this is all implicitly pi zero one, of course, but uh, embedded maximality is purely infinite. Forcing embedded maximality into finite form is what I was doing, but it's much better to do a totally competitive, in some ways nicer, but that's a matter of opinion, a somewhat competitive thing called free choice, which has an infinite theory itself, also embedded free choice, which also has embedded free choice is completely parallel to embedded maximality. They're both infinite theories. Embedded global free choice. I'll go over this later. Those are parallel developments, but embedded global free choice has a gorgeous finite form, whereas embedded maximality does not. So that's what happened. Um, and um, and also the game thing is going to be very strong, but we're not talking about that at all today. All right, so the chapters look like this: Introduction, Embeddings of Real Point Sets is the core math section chapter, and embedding maximality is what we've been talking about. Is chapter 3, which is not being changed except for certain upgrades. And then there's the reversals, which really hasn't been touched, which does have to be uh, has to have to be edited a little bit in order to match all the notation of the rest of the book. There's nothing in the core. And then there's this chapter 5 we're talking about now, which is now called finite. Oh, it's no longer called finite embeddability. It's called finite embedded free choice. No, I think I changed. No, no, no. I don't have the titles of the book right. Um, this chapter that we're talking about is just going to be called free choice because it has the infinite theory and the finite theory. So this chapter is free choice. And then game theory we haven't talked about. All right. Before getting into chapter 5, we'll discuss important developments in chapters 2 and 3. The connection between the core mathematical chapter 2 and the rest of the book has been greatly strengthened. And this is important because now it looks like there's a smooth transition from a completely, obviously, totally important and natural subject in core math into this new subject, which this new stuff, which is these large cardinals. So I now have appropriate usability notions that drive chapter 2, just as they drive chapter 3. The idea is to use subfamilies of the piecewise linear and semi-algebraic functions with upper bounds on the magnitudes of the coefficients. So this notation here has been approved by AI. uh, PLK, NQ, SAK, DNQ, PLK, NR, and SAK, DNR. Uh, I think that these are almost in use. in core math. I mean, maybe, maybe you can quibble a little bit. So, for example, S, A, K, D, and R is the semi-algebraic sets in n dimensions um, with in the reals, yeah, with n dimensions of degree at most D, uh, whose coefficients have magnitude at most K. Um no, K is the dimension, sorry. Magnitude at most N. Yeah, yeah. The subscript K is the dimension. N is the bound on the number. N is the bound on the magnitude of the coefficients. Yeah, sorry. That's what this is. All right. So, and these families have usable embeddings. In other words, there's embeddings which work for all the elements of this class. See, that's what I didn't have before in chapter 2. But anyways, we're not talking about chapter 2. I just want to say it's coming up after I finish chapter 5. Um, so this is smooths out the connection between the core math and the uh, the large cardinal stuff. All right. So now in chapter 3, I did an expositional improvement that really is important. Um, uh, I now distinguish what I call general embedded maximality and special embedded maximality. And general embedded maximality is driven by the usability concept, that we've been talking about, and the special embedded maximality just uses this one very natural specific family of functions that I write, as you remember, square brackets -1 0 open, right left close right open, semicolon 0 to divided by n to n divided by n. That is the notation used with the reversal. In other words, the reversal uses a specific usability situation. So the reversal uses a specific, and then the general theory of usable maps is this general theory. So OIEU is the lead statement of the general theory. This is not new. This is all just redoing it expositionally, re-exposition. The identity extension of every finite usable function is usable. That's the lead statement of general embedded maximality, and special embedded maximality has two lead statements. One using only one variable and the other using two variables. I think it's worth it to have both. It's the first one. This statement here that chapter 4, the reversal works on. Chapter 4 literally takes that and reverses it to con SRP. This one here is more general because well, no, it's not. It's a little different because n is not linked to the k, and but of course one shows that both of these are. Oh, I'm sorry. If I universally quantify, I take all statements are universally quantified unless indicated otherwise. That's a convention in the book. Sorry. So SEM2 is it trivially implies SEM1. You just said n equals k. Sorry. Yeah. So all three of these statements, the book, we already know all three of these statements from chapters 3 and 4. All three of these statements are equivalent to con SRP over WKL naught. And this is the infinite theory. Okay, I'm done with the discussion of chapters 2 and 3. And now we're going to talk about the main point, chapter 5. So here is a table of contents. There is this subject called embedded global free choice. This is an infinite theory. This is parallel and a competitor to and an alternative to embedded maximality. Embedded global free choice is an alternative to embedded maximality. And I show that they're very closely related, almost identical, these two subjects, okay? So embedded global free choice will have its own general and special theory and so forth and so on. And I go through that. Now, section 3, finite embedded free choice. Here I use what's called free choice, which is this is not what I want to say. I I I did it like this: 1 and 2. Yeah, sorry, 2 versions. Yeah. So finite embedded choice, free choice. I don't use the word global because I want partial functions. I want finite functions. So you'll see the why I use global. Global means that it's on the whole, that the function is on the whole. The global means the function is total. It's on the whole space that you're working on. Uh, and in finite embedded free choice is on a finite. It's partial function. So I want to keep this. This is the main point. Um, the finite theory is really the new thing. All right. So um, this is special. Okay, so this is the special part of embedded global free choice, and its version. It's two. Okay, so some infinite statement in the basic infinite statement. One of the lead statements in embedded global free choice implies the finite form. And the finite form has a parameter n, which is the length of the indiscernibles. That's the 0 divided by 0 through n divided by n. So this is the so-called forward direction that the finite statement is true, assuming large cardinals. That's what this is. And I did that in complete detail. That is a little hard to write down, and there's some issues. That was a little tricky to do. Um, because it involves some computations. All right, but this is fine, and then I have to reverse it. So I reverse it. Uh, and by the way, this statement here is the pi 0 1 statement. This is explicitly pi 0 1. The other one is explicitly pi 0 2. You'll see this later. So I need to create some machinery in order to reverse this statement. And actually, I reversed another statement, and this statement is pi 0 2 and is weaker than the other two. This one is weaker than the other two. So reversing it is better, right? So I reverse this statement. It implies what's called cis n, and these are these technical systems that I made up for this reversal. And cis n is actually equivalent to the infinite statement. That's done as a self-contained thing. But cis n is not a beautiful finite form. I mean, it's obviously a finite form and it works perfectly, right? But the trouble is, it's not mathematically compelling, right? But FEF, these are mathematically compelling. This one is not that great, not as good as the others. But the point is, it's weaker, so the reversal is better. So then I get my cake and eat it. This one, the two delicious finite forms, together with, why not this one here, this auxiliary one, throw it in, and the old cis, why not throw that in? And con SRP are all equivalent over primitive recursive arithmetic. That's what we want. And there's a whole theory of, if you fix n and move it around and calibrate how strong these are, and I won't do, I probably will add something on that. Uh, but I want to close this book. I don't want this book to take forever. So I think I struggled enough to get the right finite form. All right. I'm going to add something for computer science, some algorithm thing here, but we don't have to talk about that. All right. So what is this embedded? What is this free choice thing? This is important. Um, Embedded maximality and embedded global free choice are essentially equivalent. We're going to show that. Um, but it's only the embedded global free choice that leads to the explicitly finite forms. Uh, the simplest one is pi 02, and a slightly more involved one is pi 01, but none of them are too involved. All right, so it's most convenient to use when I do free choice, uh, it's convenient to use reflexive and symmetric relations. Such relations have been well studied. They're called tolerance relations. A tolerance relation is a reflexive and symmetric relation. See, it isn't transitive. That would be different. That would be not what you want. Okay, reflexive and symmetric. And a free set, and it's clear what a free set is. Now, what is a global choice function? This is the point. A global choice function is a function. This should be an arrow sign here. Function f from x into x. See, it's total, which chooses f of x is always related to x. And since it's symmetric, we don't have to worry about is x related to f of x. Automatically, it's the same because these things are symmetric, or tolerance relations. All right, and a global choice function, yeah, a global free choice function. Now we're talking about what we want to talk about. A global free choice function is a global choice function whose ranges are free, whose range is free. Okay, so a global free choice function is a global choice function whose range is free. This is competitive to a maximal chain, and it turns out to be uh, very, very close. In some ways, the same, but you'll see that there's some issues and some open problems that I don't want to get into in this book. Um, And so remember from chapter 3, we have general maximal chain with no embeddings in it at all. And ZFC proves it, and it's equivalent to the axiom of choice over Z. And we had so now we have general global free choice. Every tolerance relation on X has a global free choice function, and that's also equivalent to the axiom of choice. Because you can easily show it's stronger than the global free choice is stronger than the maximal chain, and therefore it implies the axiom of choice. And general global free choice can be proved using Zorn's lemma in the same way. All right. Anyways, but we want to get more detailed things because we're going to bring in embeddings. We have to show how we can go explicitly from global free choice functions to maximal chains, and also the other way. So this is the theorem that you can go from a global free choice function to maximal chains. If you want to get a maximal chain, so let R be a relation on X. We want to get a maximal chain. We go to R prime, which is a tolerance relation built out of, which is obtained by modifying R. And then if you take, then the global free choice functions for R prime are exactly the global choice functions. F is a global free choice function for R prime if and only if F is a global choice function, and the range of F is a maximal chain in R, if and only if F is a global choice function and the range of F is a chain. Okay, I probably didn't say this the best way. There's several ways to say this. Um, the other way to say it is something is a chain in R if and only if uh, okay, maybe this is the one I want to say. And the other thing is done here. I have to think a little bit carefully about how I'm saying globally that these you can go from one to the other. So here, this is the other one. Suppose I have a tolerance relation, and then I can go to an ordinary relation, and the maximal chains in R star exactly the global free choice functions for R. All right, I have to clean this up a little bit. It's just a conceptual thing. Um, the details that you want are all in here. Okay, so I didn't mean to put a proof in here. Actually, I don't do that. Okay. I mean, this is all sort of general soft stuff. There's no, you know, foundational kind of stuff. There's no kind of complicated thing going on here. Yeah, it's all smooth, all natural operations and so forth. Um, yeah, so you get this that you can prove GGFC and you can prove the equivalence with the axiom of choice. For countable relations, you can prove it in RCA naught, and for finite relations in EFA. Um, the that was the case. That was the case also for embedded maximality. The same thing. Uh, yeah, I guess I'll spend some time giving all the relationships between free choice, the global free choice, and maximality. Global free choice and maximality, or embedded global free choice and embedded maximality. Yeah, I'll clean that up a little bit because I think that it's probably a longer story. There's probably more ways to say it, different ways to say it. They're all the same. Okay. Um, okay. Now, if you just make it order invariant, in other words, global free choice theory for order invariant relations, this can be proved in uh, for order invariant relations. This can be proved in EFA in the appropriate sense because it's an infinite statements, but the point is you get an explicit example. So this happened, this was discussed in embedded maximality, that you can, that order invariance, you can actually prove the thing in EFA. All right. So now we want to do general and special embedded global free choice. Um, so again, so we have the usability concept in embedded maximality. So we also want to have the usability concept in free choice. It just means that every order invariant tolerance relation on every -1 has an F embedded global free choice function. That's just exactly what I did in embedded maximality. And it's K usable, the same thing, but we only want we want a fixed K. We're only doing tolerance relations on -1 to the K. Okay, so that's exactly the same setup we have for embedded maximality. Um, and in general maximality, embedded maximality, we seek to determine the usable F and the set theoretic assumptions that may be required to establish the usability. And in general, so this is old. This is now the new thing I said that I upgraded chapter 3 to say general and special embedded maximality. And now we do it for global free choice. And in general embedded global free choice, we seek to determine the usable free choice, FC means free choice, F, and the set theoretic assumptions that may be required to establish the usability free choice. Okay, now, in order for me to uh, do my thing, which shows that these subjects are equivalent or more or less equivalent, I need a lemma that comes up, which is a nice lemma to know on its own. If F is a global free choice function for a tolerance relation, then it's idempotent. In other words, F of X equals F of X. Uh, I think this is the same thing. Yeah. Okay. So, yeah, yeah. These two facts are equivalent. To say that it's idempotent is the same as saying this. Yeah, and I proved that. We don't need to. Nice, pretty proof that global free choice functions are idempotent. Um, okay, now one has this theorem which says the subjects are the same in some way, namely F is usable free choice if and only if F is usable. Okay, we got that. However, what happens when we fix the dimension? F is K usable free choice if and only if F is K usable. Well, one direction I know, and the other direction I have to double the dimension. So F is 2K usable implies this A should be in arrows. A stands for arrows. Um, F is 2K usable implies that F is K usable. You see, in some sense, free choice is a little more powerful. But I don't know. I don't know what whether 2K is best possible. I don't even. I'm not sure. I know that maybe it's true even with just K. So, anyways, any discussion of optimal forms or even improvements is beyond the scope of this book. However, for finite F, I can show that there's no difference, and that's because, uh, well, that's just because I don't want to get into it particularly, but I have complete analysis of the finite case, if you remember, and it carries over for this case. Yeah. Um, yeah. Actually, all right. I'm not going to say more about it. I mean, you can, yeah. It turns out that for finite case, K usable implies 2K usable. K usable implies you can raise once it's dimension two, you can raise it up, and then in one dimension, you have to do it by hand. All right. Now, I don't want to dwell on this. Okay. So recall the lead statement of general embedded maximality is OIEU, the outer identity extension of any finite usable F is usable. And now we have this, the outer extension of every finite usable free choice F is usable free choice. See, we have that. And these are all, and we can show that these are equivalent. We can show that these are equivalent. And also, if you remember, we also looked at fixing the dimension and the n in here like this. This was in chapter 3, this statement. And then we can make the same statement here, right? N is the size of the field of the function, and K is the dimension. And then we get this one implies this one, but you have to go up to double the dimension to get the other way. Okay. And the special theory, in the revised chapter 3, upgraded a little bit, we have two lead statements for the special theory. In fact, I think I mentioned that earlier. Here they are, where we use this particular natural function. This is the exact statement that is that's chapter 4 reversed. That statement, and both of them are equivalent. Okay, so now we can do the same thing over here. Get the same thing here. We get this awful acronym SEGFC1. Yeah, I may have to figure out how to make this more friendly. This long set of letters. I don't know how to do that exactly, but anyways. So we also have that, and then we have the equivalences. But again, when you have to double the dimension, you have to double the dimension when you Uh, uh, you have to double the dimension when you want to go from the embedded maximality statement to the uh, free choice statement, global free choice statement. All right, fine. Now we want to talk about the main event. And here it is, finite embedded free choice. So officially, we have to restate this. I have to tell you what a free choice function is. It's just the same. The definition is the same as a global free choice, except you get rid of you don't require it to be a total function. It's just any partial function. Here, see you remember my double colon notation. The double colon notation is means partial function. Okay. So we have this definition whose range is free, and then we're going to use special embedded global free choice as the basis uh, for finite embedded free choice. I'm not going to do any general finite embedded free choice. That's beyond the scope of this book. It's perfectly reasonable, but I'm not going to be doing it. I think I quit. I'm retiring from that. But uh, one can do that and see what happens. All right. So for readability, it's very convenient to use arithmetic progressions. So we're about to state the finite, explicitly finite forms, but I need, and it's very natural to have very special arithmetic progression notation. In fact, even simpler than any other notation because the arithmetic progressions that I care about all start from -1 and end at 1. They all go from -1 to 1. Okay, so the AP of -1, 1, semicolon M is the arithmetic progression starting with -1, ending with 1, and whose increments are 1 divided by n. The increments are 1 divided by m, and m is a non-negative, is a positive integer. That's a convention in the book also, that certain letters stand for positive integers unless indicated otherwise. So AP of -1, 1, 1/4 is this thing here with increments 1/4. All right. I think it has nine terms. Okay. All right. Recall this the second version of the lead statement in special embedded global free choice. Every order invariant relation has a blah embedded global free choice function, this particular function. So here's the two finite forms. The first one is pi02, and the second is pi01. The first version is every order invariant relation on -1, 1 to the k, so far very normal, has a blank embedded free choice function mapping all of the arithmetic progression -1, 1k to the k into its domain AP of -1, 1, 3kn factorial to the k. Right? Okay, now what am I saying? I'm saying, given an order invariant relation, obviously I have a blank embedded choice function because it could be the empty function, right? A global one, of course, is another story, and that's the infinite theory. Uh, but we've got we want to get a finite one of these functions, and we're requiring that it be defined on the arithmetic progression, this arithmetic progression, of course, to the kth power, Cartesian power, defined from that arithmetic progression into a bigger arithmetic progression. Let's call it a thicker arithmetic progression, a thicker one, which happens to also be its domain. See, it's very cleverly written. mapping all of this little arithmetic progression into a bigger arithmetic progression that is its domain, right? Okay, and then the pi 0, 1 form, that's pi 0, 2. The pi 0, 1 form is every order invariant relation on this arithmetic progression to the k, namely AP minus 1, 1 with 3kn double factorial. So it's on a super thick arithmetic progression. We got an order invariant relation on a super big arithmetic progression, super thick. It has the same kind of embedded free choice function, which maps all of this same little arithmetic progression into an intermediate one, into a middle level one. See? And of course, double factorial means factorial of factorial. And note that the first one is explicitly pi 0, 2, and the second one is explicitly pi 0, 1. Now the expressions, now just play with this. If you think about this, this is a very tightly constructed finite forms. Very tightly. Okay, now of course I use these numbers 3kn factorial and 3kn double factorial. They're chosen for immediate reability and are far from best possible. Because if I tried to write what actually the proof gives, you wind up with these horrendously ugly exponential expressions in k and n, and it just would look horrible. But also, if I didn't use the arithmetic progression notation, things would also look ugly. So how do you actually make this look completely beautiful? How do you do this? You use arithmetic progressions, and you don't care about uh, uh, exactness. You use the factorials. By the way, so obviously, beyond the scope of this book is get tighter results. But there is something else which I'm going to do, which I'm going to say, I didn't do it prepared for today. I want to create a template where I just throw around arithmetic progressions. So there's a subject, I don't know what the name of it should be. There's a subject in which I'm throwing around as a template probably keep free choice as the main glue. So I have embedded free choice. Maybe I keep this as a I keep this as a concept. Maybe I keep this as a concept, and I want to throw around arbitrary arithmetic progressions in the statement in a couple of places, or maybe in several places, or somehow, and start asking when is this true and when it isn't. I have to think about that, but that might be somewhat attractive. That this is not a super one-off thing. There's going to be a lot of other things. There's an iterated form of this, and it starts to get, of course, less pretty. But you see that this is like this is one iterate. Oh, by the way, I did finally prove, and that was going on for a while, something like this that I didn't understand. If you just say that there's every order invariant relation has an embedded free choice function defined on any arithmetic progression, and don't say anything about anything like this kicker that it goes into the domain, then you can actually prove it in RCA naught. Or, well, no, I'm not sure I could do that. You could prove it in ACA prime. In other words, it collapses to something weak. It's really the idea that you can map something substantial but small into something bigger that's the domain. In other words, you're able to continue the map. You see, you're continuing the map because this is the domain. You see. So yeah, and here's where I have three arithmetic progressions. Yeah, there's also a little arithmetic progression that's used in a different way in the embedding. Uh, so I predict that this will be turned into something a little more general about mapping arithmetic progressions into each other and something like that. I may be able to do this so it becomes very uh, uh, compelling in that way. But I think this is enough for the book. I think this is maybe some discussions, but not more work. Um, Okay, so I'm going to say something. I want to quit at 11. It's 10:44. So I do want to talk about some ingredients about what's going on here technically. So how do you prove the statement from the infinite form? This is the infinite form here. So how do you prove this statement? And by the way, I do it with n fixed. So that's, better, of course, because one does have some information. If you remember, we did this kind of thing that when n is 2, you get something like second arithmetic is enough, and some gradations like that. Although we haven't been able to do reversals except for the whole thing. Haven't claimed any reversals. All right, so uh, we assume the infinite statement, and we fix n, and we prove the statement. We let R be an order invariant relation on this. We want to prove. Sorry, we want to prove the stronger statement. Yeah, you can prove it stronger. We want to prove the pi 0 1 statement, not just the pi 0 2 statement. And then the pi 0 2 statement follows from the pi 0 1 statement. And sorry, this is not right. This would be double factorial. Uh, we extend it we can pretend that this order invariant relation is actually on the whole space here, right? And then we let F be a blah embedded global free choice function for R prime. That's what the original infinite statement says. And now we want to build we want to build some controlled finite pieces of it, right? So, uh, uh, so if A is a non-empty finite, this is a general fact that you can turn things into arithmetic progressions that weren't before. This is what this says. You can turn things into arithmetic progressions. That's what this tool is. If A is a non-empty finite set with fewer than R elements, and this is all one-dimensional stuff, this lemma, there exists a strictly increasing map from A together with some basic material, arithmetic progression -1, 1s, into AP -1, 1 R times S, which is the identity on AP -1, 1s. This is a purely order theoretic one-dimensional thing. Order theoretic one-dimensional is pretty easy, tame stuff. So you just play with this. You multiply R and S. All right, so we take the function and we apply it to AP -1, 1k to the k, and we get a set S, right? And we can get bounds on the cardinality of S in its field, and then get a strictly increasing function applying lemma 541 to it like this, which is the identity on there. Okay, so now we have part of the statement that we want to prove, but now we have to see F restricted to this to F restricted to AP -1, 1k. F restricted to this is not going to cut it yet because it's too small. We have to iterate it. We have to then extend this so it's defined on the arithmetic progression the that we're going into. We're going into here, right? The next step is we have to extend the map. We have to extend the map so that its domain is exactly this. We have to extend the map so the domain is exactly this, right? And then hope that that actually has all the properties we want, which it does. So we first extend F to be global, because any finite map can be extended to a global map that's strictly increasing uh, as a bijection, as long as the original map is defined. This is one-dimensional stuff. As long as the original map is defined at -1 and 1, which it is. So when you do that, you get an isomorphism. So the original infinite global animal, F, becomes a new global animal, G, which is still embedded and still a global free choice function, and now does map the original little arithmetic progression into this intermediate one, right? Because I did it by composing, so to speak. And it's the identity on here. Yeah, so you can do this. This should be it. There. You can do that. So that flattens it out into an arithmetic progression situation, right? So G and G remains an embedded global free choice function. That's because isomorphisms and also embedded like this. That's because isomorphisms preserves statements, first order statements. See this F star. All right. So now we work with G. We throw F in the garbage can, and we work with G now. And so we now look at G, how it behaves applied to this intermediate arithmetic progression. And we get a set T, and then we do the same thing we did earlier, really, except it's a little more complicated because the numbers are a little messier. And we get a mapping into this thickest of the third thickest, the third arithmetic progression, which is of grade 3kn double factorial, right? That many increments of one divided by that. Yeah. Okay. And then that's proved very similarly with the identity on here. And then now we're done because we can actually take G restricted to what we just did. We did restricted to the intermediate arithmetic progression. And this goes into 3kn double factorial just because of this up here and maps the first one into the second one. So it maps the second one into the third one and the first one into the second one. But I mean, it's always to the kth power. Maybe I forgot to put the dimensions in. Yeah. Uh, Whoops. Oh God, this is this. All right. How do I get out of this? Just a second. All right. View. I'm going to have to go back to view. See, I touched the mouse, the pad, and then I got into trouble. How do I get this out? Just a second. I have to escape. That's it. Escape. Okay. Now we go back to this, and now we're going to go view to this. but this isn't my file. This is the other file. Okay, so where is my big file? Um, my file with the 24 point. I couldn't have possibly. Wait. This one said, right. So this one is not the file. And this one is not the file. And did I actually close? Maybe I accidentally closed the file. Now I have to get it back. Just a second. This guy can't be hard. Just a second. Microsoft Word. Okay, I must have accidentally closed that file or something. Just a second. Where's Word? Here. Okay. All right. Hello. I'm back, I think, right?
Yes.
Okay. I just wanted to hear you say yes because I was worried maybe I lost the sound again. Okay. So, all right. So, yeah. Okay. So, okay. I only have 5 more minutes. Okay. So let me do, and I will end at 11. Uh, so, yeah. So I doubled up. Yeah, so I doubled up the function. In other words, I defined it on the first arithmetic progression, and then I changed from the global thing, and then I changed from the global choice function. Then I changed the choice function, and then threw the old one away, and then I extended the map at the intermediate arithmetic progression, and then I claim when I do that, everything is done. I maintain the embedded property, the embedded. I maintain the embedded. I touched the screen. That's what I did wrong. All right. Um, I touched the screen. That is, I don't know why that's such a bad thing to do. Um, I know why. Okay, so we're going to go to view. We're going to go enter full screen. Yeah. Okay. All right. All right. I,
No, it's not
I'm
good.
not. I'm sick of this, and what I'm going to do is actually talk to you. No more screen. So,
Um,
so the function at the end is the function that I want. It has the properties. It was defined first on the little. Don't touch the screen. I've learned this. I don't know why touching the screen is so bad. Maybe that's a Zoom feature that touching the screen is important. I don't know, but anyways, so what I'm going to do, okay, so that's the forward proof, and the reversal. I only had 3 minutes. I only had a few minutes anyway to talk about the reversal, but the reversal is done like roughly like this. I have to be very general about this, vague about this. Um, there's a thing called I call it sequential systems. I just make up a name, systems or something. These are finite approximations, crude, logic-oriented finite approximations to a free choice function. Crude, finite approximations to a free choice function. Now you can actually see me, right? Hello,
yeah,
can you see me?
yes.
Okay,
But
okay.
anyway, what I would suggest is maybe we do a second recording of the meeting today because you don't want to have this on loop,
Oh,
right?
oh, okay. I mean at night or something. I mean,
At some moment, but
okay.
let's say I don't want to put let's say these things
I see.
YouTube and I think it is also no need to hurry at the moment. We
Is
just
there any way? I mean, I'm very happy with the way I gave this talk until I got into that trouble. Is there any way you can? splice it so that I just have to.
Yeah, but then I have to study the system. So there are
Oh, okay, that's too
there
hard. We'll start over. We'll start over.
there's some possibility to modify these MP4 files.
Oh,
But first, I have to check with Google how to do it, and
here's another idea. We just do it this way. Period. And I finish it next week, and it goes on YouTube. This is reality TV. There's a thing called reality TV. Let's
yeah,
do that.
okay.
In other words, this is a historical account of not only what I did, but the problems I ran into technically, and that's also interesting because
Anyway,
people
yeah,
people
yeah,
in the future are going to be amused by it. So I think we'll leave this.
yeah.
You can cut off the you can cut the thing. You can cut the thing like it doesn't include this. You can cut the thing, but I think this is best. And then next week everything will be perfect.
yeah. Anyway,